Yeah, recording has begun. So yesterday was the end of unit 3. So today we are going to start with unit 4. So um, what is the title of unit 4? Anybody? You must be seeing the syllabus regularly, if I'm not wrong. You should be seeing it, of course. What is the syllabus for unit 4?
Isoparametric finite elements, ma'am.
Oh, good. Somebody is seeing this. Right. I'll share my screen with you. You have your syllabus on screen. Okay. Right. So this is your syllabus for unit 4. Construction of shape functions of higher order elements using natural coordinate system. That's the first thing. Next is shape functions for 8-noded parabolic curved isoparametric element. And then elemental stiffness for 4-noded quadrilateral element. Until now in the unit 3 we have seen only the shape functions, elemental stiffness, everything for until uh, rectangular elements. All right. So from now on, you're going to see about the curved elements also and quadrilateral elements also. All right. And then is use of Jacobian and Gauss quadrature techniques for what? For determination of elemental stiffness. Then the load matrix for the 8-noded rectangular isoparametric element. This will be your syllabus for unit 4. All right. So let's start with the class today. If you remember from our first, introduction for elements class, um, I mentioned about isoparametric elements. Anybody, what are isoparametric elements? Anyone? I should know whether you are listening to the class or not, right? Whoever was present for that day's class, I'm asking you, what are isoparametric elements? You're not
Curved element.
restricted. Okay, curved elements. Okay, and any more answer did I give? Any more answers? To be frank, it is not exactly curved elements, but the concept of, yeah, curved for to overcome the point that curved structures are also available and we have to analyze it. The concept of isoparametry is taken into account. Not exactly curved elements are not directly called as isoparametric, but yeah, isoparametric concept is taken to um, solve. Yes, Javeria, why are you raising your hand now?
Ma'am, my
Mm.
phone got disconnected, ma'am, so I just came back.
Mm-hmm.
So I just raised my hand.
Okay. All right. All right. So, it is like for the analysis of structural problems when complex shapes are involved. When complex shapes are involved, uh, to overcome or to um, analyze that complex shaped structures, what all concept we were seeing till now for CST element or rectangular element, Lagrange's model, all these things are not sufficient when it comes to curved boundaries for the complex problems or the shapes also. If you see, until now whatever we have seen, Lagrange's or serendipity or anything, you could see that it is the standard shapes what we have seen. We didn't look into the quadrilateral type of element or anything when they are not in 90 degrees, how it goes. All right, all these things. So to overcome all these parameters and to analyze the structure in whatever form it may be, curved, inclined, all right, combined, so to analyze all these, what the concept of isoparametry is actually began. All right, so who are these people responsible is, I'll share the screen here. Right. Right. Unit 4, isoparametric elements. Alright, the isoparametric concept was brought out by two people. Alright, one is Stake and the other one is Irons. Those are the people's names, okay? You may please note it down. The isoparametric concept brought out by Take and later generalized by Irons revolutionized the finite element analysis and helped in properly mapping the curved boundaries. The concept basically was brought into account that there is not always the straightly connected or the elements connected at 90 degrees only, but there are curved structures present. So how to analyze that? That is by elaborating or introducing a new concept that will help analyzing the curved type of structures also. All right, please note it down. The concept of isoparametry, the concept of isoparametry or isoparametric elements is based on the transformation of the parent element, in local or natural coordinate system, to an arbitrary shape in global Cartesian coordinate system. Let me show you how it looks. See, are you able to see the screen clearly?
Yes, ma'am.
Yeah. So here what you see is the God, it's not responding. Right. Right. Here if you see, this is the 6-noded triangular element. Alright, this we are calling it as parent element. It may be in natural coordinate system or it may be in the local coordinate system. Alright, this parent element is taken into picture and it is mapped with an arbitrary element, arbitrary shape. If you clearly see, this is not really a 6-noded triangular element. We are not calling it as triangular element, but a triangle like structure, but with curved sides. Alright, so this is the mapping that is done to the global Cartesian coordinate system. Alright, so this is the concept based on our parent element, what all shape functions we already know. From that we are going to map that to the elementary shape. Alright, arbitrary shape. Alright, see, if you see many other types of isoparametric elements, see, rectangle to the quadrilateral is also like that. It need not be the curved ones only. This is the parent element here, four noded rectangular element to the left, and the mapped arbitrary shape is to your right, quadrilateral. Alright, not curved yet. If you see the next figure, 8 noded rectangular element, alright, is mapped with 8 noded with what? The sides are of quadric curved nature. Parabolic, quadric, cubic, quartic, all these things we have seen. Alright, these are mapped to quadric curved structure. Alright, so based on what we already know, or how we have the shape, we have derived the shape functions, taking that as the base, we are trying to relate that to the arbitrary shape with the curved surfaces. Did you understand the point what I'm trying to tell? Any doubts in this part? See, even if it is not just for 2D, it can be elaborated to the 3D also. Alright, see, all these things are, all these pictures what you see on screen are isoparametric elements only. This picture is from the Bhavikati textbook. Alright, I have posted Bhavikati textbook already in the files section. Alright, did you understand how is the isoparametric concept done? Any doubts so far? Are you with me, guys?
Yes, ma'am.
Yeah.
Yes,
To be
ma'am.
frank, it is only about 2 derivations and problems. We can end our unit 4. Please try to concentrate it. All right. Now, in the previous cases, we saw we are going to have a parent element, and then we are going to have a mapped element. 2 different elements that we are going to have. Now, from parent element, if we see, we have parent element, and then we have mapped element, which is isoparametric. Okay, mapped element. Now, from parent element, what do we have? We have shape functions available. Alright, through shape functions, what are we trying to find out? We are trying to find out deflections through shape functions. Alright, that is in terms of nodal displacements. We are trying to find out. Now, to the mapped element using these 2 factors, shape functions and the deflection, nodal displacements. Alright, using that we are going to analyze the mapped element. This is what we are doing till now. We have shape functions with us, we have nodal displacements to it, and then we are trying to analyze it. Okay, now how are these both going to be related is the concept of isoparametric. Alright, please note down a point, then we can start continuing with the topic. The shape functions are used for defining deflection. Shape functions are used for defining deflection at any point in terms of nodal displacements. In terms of nodal displacements. Take suggested. Take is the person who was the one who brought the isoparametric concept into picture. Okay. Take suggested, TAIG. Take suggested use of shape functions. Take suggested use of shape functions for coordinate transformation for coordinate transformation from natural or local coordinate system from natural or local coordinate system to global coordinate system to global Cartesian system to global Cartesian system and has successfully achieved in mapping the parent element in mapping the parent element to required shape to the required shape in the global system in the global system. Now how is that done? Look here, we have two things. One is parent element and the other one is mapped element. Okay, what we'll do is first we will consider the rectangle 4-noded rectangular element as our parent element. 4-noded rectangular element 1 2 3 4. What are its coordinates? We know. Well, let us take this in the natural coordinate system, because we already know them. 1, 1, and then finally -1, 1. -1, 1. And then we have centroid of the rectangle as origin for the natural coordinate system. Alright, suppose for this parent element, let us think that there is a point here, alright, which is P with some value of xi and eta. Alright, now we are trying to find out this point. We will try to relate this parent element to the mapping. Okay, we will map this to a quadrilateral element in the considering that as an isoparametric element here. Okay, so global Cartesian system, let us take this as x, y and the quadrilateral structure. Right, let us take this as same scene. The nodes what we have taken for the parent element are going to be reflected as same. Okay, this is 1, this is 2, this is 3 and this is 4. Now, but the global Cartesian system is x1, y1, x2, y2, x3, y3, x4, y4, and the point still remains the same, that is P, but Cartesian system is coordinate system is same, so different, so P of point x comma y. All right, now how are these both related? How is that relation taken? Is, did you take down the picture, everybody? I am not continuing the class unless I get any response.
Yes,
I'm
ma'am,
not
taken.
thank you. I'm not here to blabber in myself, okay? I need your answers. Right. Now I need to express P comma Y. P point P x comma Y. So how will I take that as? Cartesian coordinate of a point Cartesian coordinate of a point P. Here it is P. You need not write it also. In an element may be expressed as x is equal to, we know already shape functions is the one that is relating from one point to the point inside the element with the nodal points. That is what is the shape functions, if you clearly remember. So here if we take n1 x1, n2 x2, n3 x3 plus so on. Here it is 4 points, but that is not what we are seeing, right? Xn, this is what is the Cartesian coordinate of a point P. Let us not take it as P. At any point, if we consider, at any point inside the element is related to the nodal unknowns in this way. Y is equal to n1 y1. If you don't remember this equation, please turn your pages back to deriving shape functions. Okay, n n y n. Okay, because we are taking it in the Cartesian coordinate, you can name that as n dash 1, n2 dash or anything, but shape functions are the same. Now if at all it is only 2D element, this is the case. If it is a 3D element, we are going to have a x coordinate also. So n1 z1, n2 z2, and so on up to nn zn. Understood what we did here? If you remember, what are the shape functions? What exactly the shape function? Definition of shape functions you can see. The shape function is the one that relates the point inside the element, anywhere inside the element with the nodal points. Alright. So if at all I need to write this in a simpler format. That is, I can write this as x is equal to shape function matrix into coordinated nodal points, where n is the shape functions, matrix shape functions in natural coordinate system. and xe is the coordinates of nodal points of the element. Coordinates of nodal points of the element. Are we done? Did you write down? N is shape function and xe is the coordinates of nodal points of the element. Please give me a yes if you wrote it.
Yes, ma'am.
Okay. If we see the parent element exactly, and in the natural coordinate system, we already have what are the shape functions for that. Don't we have? Do we have the shape functions or not for a four-noded rectangular element in natural coordinate system? Do we have the shape functions or not?
Yes, ma'am.
Yes. Are they the same thing that I'm writing on the board now? Is this the same thing?
Yes, ma'am.
Alright, please note down the equation. Now based on this equation, what are all the shape functions from n1 to n4? That also we have. You may note that shape functions also. Did you write down all the four shape functions?
Yes, ma'am.
Okay. Now we all from the figure if you see point P is of coordinates xi comma n. Alright. And we have in GCS, that is the global Cartesian system, in GCS the nodal points are like this. Nodal points are x1 y1, x2 y2, x3 y3, x4 y4. Alright. Now based on this, how is it related to if you see this relation, taking this into account, to get the mapping, we define the coordinate of the point P. We define the coordinate of the point P. We define the coordinate of the point P as x is equal to, how many do we have here? n1 x1, n2 x2, n3 x3 plus n4 x4. Similarly, y is equal to n1 y1, n2 y2, n3 y3, n4 y4. So this can be rewritten as x is equal to summation of ni xi and y is equal to summation of ni yi. The point here is, let us take this equation. Let us take this whole thing, two equations of x comma y. as equation 1. Till now, from the definition of shape functions, we only know that shape functions are used to uh, define deflections, all right, at any point in the element with the nodal unknowns, that is the displacements at the nodes, all right. But what Tag has done is he has taken that into picture, I mean that into account, and used the same shape function to define geometry also, all right. Shape functions are now used to define geometry when it is about the isoparametric elements. What is it? Any point or any coordinate, any point inside the element for the mapped structure P x comma y can be known by the nodal points of the mapped structure. If you know the vertices of the nodal points, from that also we can get what is that point inside the element. Understood? But what do we need? We need the values of shape functions. Did you understand? Did you understand until this point? We know what are the um, properties of shape functions already. Shape functions are, uh, if at all at one particular node you're taking, at that particular node it will be unity, and all the other nodes where you're calculating for the shape, for deriving the shape functions, it will be 0. Same as of stiffness. All right. And the convergence criteria of the parameter of the element or the displacement model what we are taking also has to be satisfied. All these things what we have learned till now for the triangular element, rectangular element, all these things are taken as it is when it comes to isoparametric concept. Just understanding that the shape functions what we use till now to use deflection is also used to define a geometry when it comes to isoparametric. Until now, until unit 3, it is that shape function, using shape functions we can find out nodal or the elemental displacements. But from unit 4, from when it comes to isoparametric concept, shape functions are used to define deflection, plus they are also used to define, also used to derive geometry also. Got the point? Any doubts until this point? Any doubts until this part? Any doubt until this part? Any doubt until this part, guys?
No, ma'am.
Is there any lag coming here? Because I'm getting your answer very late. Alright, now in isoparametric also, I don't want to waste the time because we are lacking much time already. We have to complete the syllabus before 15th of February, because you have your unit test mid 2 at Feb 15th. Right. Now, in isoparametric elements, there are 3 different elements there in under isoparametric. One is isoparametric directly. Okay. So, isoparametric elements, and the other one is superparametric, and the other one is subparametric. Isoparametric, superparametric, and subparametric. I already said you that here in isoparametric concept, shape functions are used to define geometry and displacements. Is it not? Now, see. Supposedly, I have some element like this, curved structure or curved element. All right. Now for this, I have nodes 1, 2, 3, 4, 5, 6, 7, 8. All right. And 1, 2, this is just a representation, okay? See, where we have these two. Let us take this as the shape functions used for defining displacements and shape functions that are used to define geometry. All right. I'll give you time to note down the picture. Not shape functions, you can write this as nodes. Okay. Displacement nodes, nodes defining displacements, nodes defining geometry. Okay. Now, when are they called isoparametric is when the nodes that are used to define geometry are equal to the nodes that are used to define displacements. The thing is, here the boxes what we are seeing, to be frank, simply in the figure like that it is. The nodes that are used to define geometry, when they are equal with the nodes that are used to define the displacements, then we are calling that as isoparametric. You may note down the definition or the statement, please. I'll put that on screen for you. Are you able to see the screen now? Are you able to see the screen?
Yes, ma'am.
Right. Look here. All the three pictures are here in front of you. Nodes used for defining geometry, nodes used for defining displacements. Isoparametric is here you have. See. Shape functions defining boundary and the displacements are same. Then we are calling that as isoparametric. Shape functions defining the boundary and the displacements are equal or same are called isoparametric elements. Okay, what's wrong with this? Something wrong. All right. Let's take the figure then. This is another parametric element. These are the nodes that are defining the geometry. And these are the nodes that are defining the displacements. if the nodes that are used to define geometry are more when compared to the nodes that are used to define the displacements, then we are calling that as superparametric element. The elements in which, write down the elements in which more number of nodes are used to define geometry when compared to the nodes used to define displacement, when compared to the number of nodes used to define displacements. Such elements are called superparametric elements. Superparametric elements. So what do you think are subparametric? What are subparametric? You can give a guess. Try giving a guess.
Comparatively less number of nodes.
Of what? Which one? Which ones are less?
Nodes that define property are less, ma'am.
Property. There are no nodes that define property here.
Geometry.
Okay, good. That's right. The elements in which the number of nodes used to define geometry are less when compared to the nodes that define displacements is called subparametric elements. If you see your previous year question paper, this was asked for 2 marks. It will be asked, you have to show it with the figure. Draw a figure, show the differences between the nodes that are defining geometry and the nodes that are defining the displacements, and then give the answer. That will give you full marks. They may ask you for 5 marks also. We never know. All right. Are we done with this one? Are we done until this part? Are you clear what is isoparametric, what is superparametric, and what is subparametric?
Yes, ma'am.
Okay, thank you. Right. If you see the figure here, we are going to talk about this figure only. From the parent element, what we have taken, we have 4 shape functions. Now we will try to assemble stiffness matrix for this quadratic element. All right. Right. Assembling of a stiffness matrix. Assembling of stiffness matrix. To assemble stiffness matrix from equation 1 using shape functions for geometry. Geometry indicates x comma y. Is it not? n1 0, n2 0, n3 0, n4 0. Is the screen visible properly? I think it is small. Right. Zero n1, 0 n2, 0 n3, 0 n4 with elemental nodal points, that is x1 y1, x2 y2, x3 y3, x4 y4. What is this here? This is the shape functions that are used for geometry. Let's take this as equation number A. Okay. Now, but from the beginning, we already know when it is about what the shape functions is. Shape functions is the function that relates the nodal displacements to the displacements anywhere in the element. Alright. Now for defining shape functions, the displacement at any point in the element. At any point in the element, if the displacements have to be calculated, what is that going to be? N1 0, N2 0, N3 0, N4 0. 0 n1, 0 n2, 0 n3, 0 n4 with the nodal displacements u1 v1, u2 v2, u3 v3, u4 v4. Let this be equation number B. Now what is this here? This is shape functions for displacements. Alright. Now for assembling the stiffness matrix, we need derivatives of shape functions. If you remember, how would we assemble the shape functions? We do the partial differentiation of the shape functions to get the value of k. Alright. Now in assembling the stiffness matrix, we need the derivatives of displacements with respect to x comma y, that is the global coordinate system. What I'm trying to tell you have to understand. That is why unit 3 is very important that you be present. Alright. So derivatives of displacements with respect to x comma y will only help us to get the stiffness matrix. What is stiffness matrix? K matrix is B transpose into D into B into dV, triple integration to volume. Alright. So now if at all I need the B matrix, that is the strain displacement matrix. Strain displacement matrix includes derivations, differentiation of shape function with respect to x comma y. Are you getting the point? I really think you must be keeping blank faces already. K matrix is this not the K matrix we know? Is this the K matrix we know? Stiffness, elemental stiffness. Are you guys there in the class?
Yes, ma'am.
Oh my god, only one yes. It's like all of you are sleeping. In here, D matrix we can get it depending upon the plane stress condition or plane strain condition. But in the B matrix, we have derivatives of shape function. Either it may be with respect to x or it may be with respect to y. we have derivatives of shape functions. But what with respect to x comma y? Now what is x comma y? They are the global system. Alright. Now if we need that, it is easy to change it from local coordinates. If to do the derivatives from local coordinate system to the global coordinate system, it was easy. Alright. But when we have to do it with respect to global Cartesian system, we need to take the help of the partial chain rule of partial differentiation into picture. That is, we have to introduce Jacobian matrix to get the derivatives from the local shape functions from the natural or local coordinate system to the global Cartesian system. Now I hope you remember what is Jacobian matrix. If you don't, we are doing it here, no worries. Right. See, write down the relation between the coordinates can be computed. The relation between the coordinates, that is, we are trying to relate the natural coordinate system or the local coordinate system to the global Cartesian system. To relate that can be computed using chain rule of partial differentiation. Chain rule of partial differentiation.
Ma'am, repeat it, ma'am, once.
The relation between the coordinates, the relation between the coordinates can be computed using chain rule of partial differentiation. Sorry, the chain rule of partial differentiation. Now what is chain rule? You know. Alright. See here what I'm trying to do. I'm trying to relate, this is in the natural coordinate system, and x comma y are in a global Cartesian system. Alright. So using chain rule, I'm trying to relate it to this. I'm trying to relate xi with x. Similarly, eta with y. Not x, x comma y. Xi with x comma y, eta with x comma y. Chain rule. Did you understand how did we do this? Chain rule. This is x here, not eta. Now, if at all this is taken in the matrix form, dou by dou xi, dou by dou eta is equal to dou x by dou xi, dou y by dou xi, dou x by dou eta, dou y by dou eta, and then we have dou by dou x, dou by dou y. See, here you can see the clear, this is in NCS and this is in GCS. So the one that is relating from relating NCS to GCS, this is called Jacobian matrix. It's called Jacobian matrix. So simply this can be written as dou by dou xi dou by dou eta is equal to Jacobian matrix into dou by dou x dou by dou y. Jacobian matrix concept is not new. Alright. So let us take this one as equation number 2. Now when we know what is Jacobian matrix, it is easy for us to either take it from GCS to NCS or from NCS to GCS. The point is we have to know what is the Jacobian matrix for any element. Alright. Now we'll take that for isoparametric element. Alright. So are we clear until this point? Are we clear?
Yes, ma'am.
Yes, ma'am.
Okay. Now for isoparametric quadrilateral element, isoparametric quadrilateral element, what do we have? We have J matrix as, let us take this as J11, J12, J21 and J22. Alright, where J11 first term is direct relation dou x to xi, J21 dou x to eta, x to eta, J12 dou x to, dou y dou y by dou xi, J22 dou y by dou eta. Alright. Now either we have to take, now what is happening here? X is being differentiated with respect to xi. We already know from equation number, what did we take that equation as? Equation number 1. Check what is equation number 1 and tell me what is the value of x. What is x? Array, you're taking so long. Summation of nixi. Is it not? Did you have this equation?
Yes, ma'am.
Right. Now when I have to find out J11, what does that mean? It means I need to do the partial differentiation of x. That is partial differentiation of x with respect of dou xi. So what will this become? Dou n1 by dou xi into xi plus dou n2 by dou xi into x2 plus dou n3 by dou xi into x3 plus dou n4 by dou xi into x4. Why the partial differentiation is applicable only for n is the terms n are with xi and eta. Is it not? X is the constant here. X values x1, x2, x3, x4 are the vertices. But the values of n are the terms with the xi and eta. So similarly you can get it for n j11, j12, j21 and j22. All right, taking all that into account, let's see, similarly you can get j12, j21 and j22. Right, taking this in a smaller form, what I can write is j11 can be written as summation of ni by dou xi into xi. So what will be j12? What is j12? Now because you're talking only about what quadrilateral element we have taken, we can write this as 1 to 4. Summation of I is equal to 1 to 4 ni by dou xi into yi. Is it not? Did you understand how did we get the Jacobian terms? I'm not moving forward until you respond.
Understood, ma'am.
Any doubt until this point?
No, ma'am.
Anyone? Anyone? Good. I assume that everybody understood. I cannot help if you don't tell it. Alright. Therefore, the Jacobian matrix can be written as summation of I is equal to 1 to 4 n1 by dou xi ni xi. Summation of I is equal to 1 to 4 ni by dou xi yi. Summation of I is equal to 1 to 4 ni by dou eta xi. Summation of I is equal to 1 to 4 ni by dou eta into yi. So let's take this as equation number 3. Alright. Now, we have already seen from equation number 2. Is this equation number 2? Is equation number 2? Yeah, from equation number 2 only. From equation number 2, what do we have? We have from equation number 2 dou by dou xi dou by dou eta is equal to Jacobian matrix into dou by dou x dou by dou y. Now if we see, we related the natural coordinate system with the global Cartesian system. But what exactly are we trying to do in the isoparametric concept is the element that is there in the natural coordinate system is being transformed into the global Cartesian system. So from this we can get it. If at all now I need the coordinates of natural coordinate system, I can use this equation directly. But if my unknown is x comma y, that is the global Cartesian system, then what I need to do? I need to take the inverse of Jacobian matrix. is equal to J inverse of dou xi dou by dou eta. Because we have our parent element in xi comma eta, we will have, this would be the given data for us. Alright. Now what we have to find out will be in the LHS side. And what we already know will be in the RHS. Alright. Now what are these terms in the inverse matrix? When you already have the Jacobian matrix with you, taking that inverse will give us these terms. Alright, this can be rewritten as I dou xi dou by dou eta. Oops. Dou by dou x dou by dou y is equal to, this is just the representation, okay? When we solve a problem, you will understand what did we actually do. But I hope here until now that's not a difficulty to understand. It's easy. All terms we have already seen. Simple matrices these are. Let us take this as equation number, is it 4 or 5? Equation number 4. Equation number 4. Alright, where are the elements of Jacobian inverse matrix? Are the elements of Jacobian inverse matrix. Jacobian inverse matrix. Alright, now we have the relation between the global Cartesian coordinate system to the natural coordinate system. Alright, now when we have to find out the displacements of the transformed relation, what we'll do is, taking equation 4 into account, for this is a 2D element, right? We need displacements now. So dou u by dou x, dou u by dou y, dou v by dou x, dou u, dou v only, right? Dou v by dou x by, next dou v by dou y. This is the displacements what we have to find out, basic unknown. This is 4 by 1 matrix will be equal to, here we need the Jacobian matrix that is relating the global Cartesian system to the natural coordinate system. What we have from, we are taking this from equation number 4, right? What here, if it is u, here it is going to be u again. So dou u by dou xi it becomes dou u by dou eta, dou v by dou xi, and dou v by dou eta. What are the terms that we are going to get here? J11, J12, J21, J22. Again J11, J12, J21, J22. Elements of inverse matrix. This is 4 by 4 matrix. This is 4 by 1 matrix. Ultimately, what we'll get? We will directly have the relation of displacements in the GCS system with the displacements in the Cartesian global Cartesian system within natural coordinate system. Any doubts until this part? Any doubts until this part? Any doubts so far?
No, ma'am.
Right. Now, once we have the elemental stiffness matrix, what is next? If at all we have to find out stress and then strain, all these things if we have to find out, the next term that comes into picture is, oh, what happened? Sorry. The next term that we have to look into is strain displacement matrix. Strain displacement relation, or the B matrix for the isoparametric, that we should see. All right. Strain displacement relationship for isoparametric elements. Now, what is strain given by? We are talking about 4-noded rectangular element as the parent element taken into isoparametric concept. So the strains are 3: epsilon x, epsilon y, gamma xy, have to be written in form of the displacements, dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y. You can check this equation from the previous classes, you can get it. 1 0 0 0 0 0 1 0 1 1 0. Okay. Now if we need the shape, the strains here, we have this one from the equation 5. Substituting equation 5 here, what do we get? Strain matrix is equal to J11 star, J12 star, 0 0 0 0, J21 star, J22 star, J21, J22, J11, J12 into dou u by dou xi, dou u by dou eta, dou v by dou xi, dou v by dou eta. This is equation number 6. This is the strain displacement relation. Strains are related to the displacements using Jacobian inverse matrix terms. We should be remembering all these equations for us when we have to solve the problem. All right. Now further, this matrix is even reduced. Why? Because here we have u and xi terms, alright, which are partially differentiated. U and v are partially differentiated with respect to xi and eta. We already know what is u and v from the previous cases. U, displacement at any point in the element, is the summation of shape function with the elemental displacement of the nodal displacements of the element. V is equal to I1 to 4 Ni Vi. If we consider these two equations and resubstitute in equation number 6, it is going to be elaborated more. What is this going to become? Just first we'll try for dou u by dou xi, dou u by dou eta, dou v by dou xi, dou v by dou eta will be equal to, what is it? Dou n1 by dou xi 0, dou n2 by dou xi 0, dou n3 by dou xi 0, dou n4 by dou xi 0 into, why is it that we have zeros in middle is? In between is, we are taking u1 v1 u2 v2 u3 v3 u4 v4. So what is this going to be? Dou n1 by dou eta 0, dou n2 by dou eta 0, dou n3 by dou eta 0, dou n4 by dou eta 0. The next terms 0, 0, dou n1 by dou xi, dou n1 by dou xi 0, 0, dou n2 by dou xi eta, dou n2 by dou eta 0, 0, dou n3 by dou xi, dou n3 by dou eta 0, 0, dou n4 by dou xi, dou n4 by dou eta. Let us take this as, what is the previous equation we have? Equation number 6. So let us take this as equation number 7. Now what do we have? We have, I'll reduce this a little for us to go to the previous one. See, what we have here, this term is the matrix here. So we need to substitute this here now. Substituting equation number 7 in equation number 6. Write down, substituting equation number 7 in equation number 6. Substituting equation number 7 in equation number 6. What do we get? I'll write it in this way. Strain matrix is equal to J21 to 2, J21, J22 star, J11 star, J12 star. That's the first term we have. Then this is of 3 by 4. Here we have dou n1 by dou xi, dou n1 by dou eta, 0, 0. Dou n, sorry, zero, zero, dou n1 by dou xi, dou n1 by dou eta, dou n2 by dou xi, dou n2 by dou eta, 0, 0, 0, 0, dou n2 by dou xi, dou n2 by dou eta, dou n3 by dou xi, dou n3 by dou eta, 0, 0, 0, 0, dou n3 by dou xi, dou n3 by dou eta, dou n4 by dou xi, dou n4 by dou eta, 0, 0, 0, 0, dou n4 by dou xi, dou n4 by dou eta, into, this is what? 4 by 8 matrix. And then finally what we have? U1, V1, U2, V2, U3, V3, U4, V4, which is 8 by 1 matrix. Now strain is related to displacement with this matrix in between. So what is this matrix called? What is this matrix, guys? Strain is related to displacement using this matrix in between. What is this matrix called?
Jacobian.
Array. Strain to displacement.
Relative
Constitutive matrix is D. I'm asking you strain to displacement. Strain displacement matrix B. Do not forget. So our strain displacement matrix, let us take this as what was the previous equation number we have taken? 7. Let us take this B matrix as equation number 8. Now we have B matrix with us. Depending upon the condition of plane stress or plane strain, we are going to get the D matrix also. So finding out the elemental stiffness will not become difficult when we have the B matrix, that is what we have seen in equation number 8, then the D matrix depending upon the plane strain or plane stress condition, next is B, and then dV. All right. Now for this case, taking thickness as T. If T is the thickness, T into 2D element only, no? So B transpose D B matrix dou X into dou Y. Okay, taking T as thickness. Now what is this dou X and dou Y? We know that is the partial differentiation of X comma Y. Alright, so dou X into dou Y is the determinant of J into dou xi into dou eta. Alright, so finally what will the elemental stiffness matrix become? Thickness into double integration of B transpose D into B det of J into dou xi into dou eta. This is the elemental stiffness for an isoparametric element. Equation number 10. Alright, now see, if you see, we have so many matrix inverses, transposes. We need to find out the matrix multiplication. All these things are so many in this one equation. Alright, so when we have to solve the problems to reduce the difficulty level of doing the multiplications and integrations in this, first we have to do the inverse, then to the multiplication, then the integration. Alright, so reducing all these things, we use a numerical integration. That is, we take Gauss quadrature into picture. Alright, using Gauss quadrature formula, we will reduce this level of difficulty and try to solve the problem. Alright, I really think this has become huge for today. Is it not, or shall we continue? If you're not full, we'll continue.
Enough, ma'am.
I know, it's very tiring. All right, I'll close the session at this point. What we have done until this part, please try to understand. If you have doubt, come back with doubt for the next session. We will solve problems on this, and once, if after solving the problems, if we just try to see the elemental stiffness for a 8-noded curved isoparametric structure, we are done with unit 4. Alright, so hardly in the next session, if we completely give our 2 hours of time, we can complete unit 4. Then unit 5 is axisymmetric elements, same as this. Taking base as our unit 3, we will continue with unit 4 and unit 5. That is why I said you have to concentrate more on unit 3. Alright, so we'll stop this here. If you have doubt, please go through that. You can find this in both of the textbooks, Chandrapatla and also from Bhavikatti. If you have doubts, you please come back with doubts, get it cleared. Because once you understand the concept, there is nothing more easy than this. The only thing is you have to be very attentive about multiplications of matrices, what is the order and how you take it. Which coordinate system are you doing it? Alright. Thank you, Tejasvi, for being the moderator today. I'll stop the recording.